This is part 4 of the series Calculus Prerequisites. In this part, we're going to start out with the rational zero test. Now, as you recall from your pre-cal and algebra 2 days, that the rational zeros test allows us to determine what the potential rational zeros would be for a given function given the coefficients of that particular polynomial function. So it says if we have a polynomial of this form, which is just a standard polynomial, and that polynomial has integer coefficients, then if this function has rational zeros, every rational zero will have the form p over q, where p and q have no common factors together other than 1, and p, the numerator, is the factors of the last term, and q, the denominator, is a factor of the first term. Now, this may have been confusing to you when you saw it before. Let's take a look at a quick example just to clarify. Here we have just a standard polynomial function, and we're saying with the rational zeros test that if this function has rational zeros, that they will be made up of a fraction which are plus or minus the factors of 12, put the factors of 12 on the top, and the factors of 1 on the bottom. 12 being the p, that is the coefficient or the constant term, or the coefficient of the last term, whichever the last term to the right is. In this case, it's 12. And the q, the denominator, being the leading coefficient of the polynomial. So what we would have is factors of 12 are going to be 1, 2, 3, 4, 6, and 12. All of those integers go into 12. And the factors of 1, of course, are 1. So what we're saying is if this function has rational zeros, they're either going to be 1 plus or minus, 2 plus or minus, 3, 4, 6, or 12, all plus or minus. It doesn't have to be any of these, but if it has rational zeros, it's going to be one of these. So let's just see if this in fact has any of these as rational zeros. We're going to use the factor theorem to do this. So what we're going to do is we're going to evaluate this function at each one of these values to see which one has a remainder of 0. If it has a remainder of 0, then it's a 0 of the function. So let's bring up a calculator here. Now let's go ahead and enter our polynomial. So it's x to the 4th plus 2x to the 3rd minus 7x squared minus 8x plus 12. Now I could do this manually, but I don't want to waste the time. And if you don't have one of these calculators, then you just have to go ahead and do that manually. But we're going to go ahead and change this to ask mode. We're going to go down here and change it so that we can enter in the independent variable manually. And we're going to evaluate this function now at each one of these values. So let's put in a 1. And we see that a 1 is a 0 of the function. Let's try negative 1. A negative 1 is not a 0 of the function. Let's try a 2. A 2 is a 0 of the function. So we know that 1 and 2 are zeros of the function. And you can continue going on with this process and see if there are more than just the ones we came up with. Generally speaking, if you want to actually go ahead and factor this, you would run through this list, and as these numbers, if these numbers start diverging, that is, if the numbers start going increasingly positive or increasingly negative as these values change, then you know that you're not going to have any further zeros for this function. So you're going to have to use some other mechanisms to factor that. But in this case, we have 2 of them already, which means we can take this quartic down to a quadratic, and if there are no more that we can get with the factor theorem, we can just simply use quadratic formula. And we're going to be working with that in a short time here. But this is how you use the rational zeros test. So let's try and do this one more time with another example to make sure you get the idea. So here we have another polynomial, and I need to factor this polynomial. We know that there's going to be 4 factors here. They may not all be rational, but let's see if we can pick out some rational zeros. We look at it first, and on the surface it doesn't look like it's going to lend itself cleanly to a factor by grouping or anything of that kind, unless it's intuitively obvious that it is. In my opinion, I'd be just wasting my time. It's much quicker to go through rational zeros and the factor theorem to find some zeros than it is to work through those algebraic methods if it's not forthcoming immediately. So let's use the rational zeros test. I know that if this has rational zeros, it's going to be factors of 18 divided by factors of 2. So we would have plus or minus factors of 18, which would be 1, 2, 3, 6, and 18. And then factors of 2 are going to be 1 and 2. Now what this tells us is we could have a factor of 3 halves. So this is an interesting little aside. Now, doesn't necessarily mean it's going to have a factor of 3 halves, but that's a possibility here because of the way the rational zero test came out. So let's go back to our calculator and see which one's which. I've gone ahead and entered the function in just to save time. So now let's go to our table and we can start entering values. So let's try 1. Don't know what that was about. 1 is not it. Let's try -1. So -1 is a 0. So we know that -1 is a 0. Let's go ahead and write that down. And let's keep going, see if we can get any more here. Let's try 2. And 2 is a 0. So we now have 2 zeros of this thing. Let's keep going and see if any more. Let's try -2. Let's try 3. -3. Oh, and we got a -3 as a 0. And let's try 6. And -6. No, let's try 3 halves. No, let's try -3 halves. Oh, and -3 halves is a 0. So we know that our zeros are 1, 2, -3, and -3 halves. Now this was a very lucky happenstance. It doesn't often come out that all of your zeros are rational zeros. In this case, it worked out that way. Just a nice easy example. So what we have here is we have 1 0 is -1. That means one factor is x plus 1. In other words, since x plus 1 equals 0, x has to equal -1. That's how this works. So if x equals -1, solve this, move the value over to the other side, and we have x plus 1 equals 0. So our factors are going to be x plus 1, x minus 2, x plus 3, and the last one is going to be 2x plus 3. So in case you didn't see that last one, it took me a second to do it in my head here. This is saying x equals -3 halves. Multiply both sides by 2. 2x equals -3. Add the 3. 2x plus 3 equals 0. So there's our factor. That's how I got this one from that. So there are our factors. And these factors multiplied together will give you this polynomial. And that's rational zeros test. Now we're going to move on to a different set of skills, And that's going to be more algebraic in nature, and we're going to be looking at complex fractions. Now, we may need to have to use some of these tools that we've already looked at to execute these complex fractions or simplify them, but let's take a look and see what we've got here. Now, our ultimate goal in all of these exercises up to this point is simplification. Rewriting, reworking expressions to put them into terms that are easier to work with in certain circumstances. Here, we're going to try and simplify these fractions to put them in the simplest form. And the way we do that is to create, in the case of a rational expression like this, is to create another expression that has no common factors other than 1. And so we're going to need to simplify this as far as possible. When we look at this, we can see that this is simply a rational expression with a common denominator already. In that case, that's all we really have to do is combine these, because we're just adding two fractions with like bases. It's like saying 1/3 plus 3/3, which would be 4/3. So that's what we're dealing with here. So that's a fairly straightforward one, and what we get to then is x minus y plus 6x minus 3y all over 8y. Simplifying this gives us x plus 6x is 7x. Negative y minus 3y is negative 4y all over 8y. Now please don't make the mistake of thinking that because we have a y down here and a y up here that we can separate these out. We cannot do that. Because of this sign in here, you can't cancel the y's. That's an illegal operation. The only way you could do it is to do it over here, and that doesn't work even in this case because we still have a binomial up in the top of this fraction. So you can't cancel out these y's in any case. So this would be our final form. There's no common factor here other than 1. There's no common factor between the numerator and denominator for all these terms. So we can't factor this any further. All right, let's go on to the second one here. Now, in this case, we have dissimilar denominators. So what we're going to have to use is the old technique, this times this times this, using that sign, divided by this times this. So we have 6 times 4, which is 24. Then we multiply this by this, and we use this sign. So it's x times 5x, which is plus 5x squared. Then negative 1 times 5x, which is minus 5x. All over 4 times x minus 1. Now you notice I didn't multiply those through, because as we said, we're trying to factor out as much as possible. So it's always a good idea to leave this unmultiplied in case you may have some cancellation opportunity. And if not, this is still in final factored form, so we'd be done with it. So let's combine this into a cleaner form. 5x squared minus 5x plus 24 over 4 times x minus 1. This quadratic has no common factors, and this is as far as we can go in the denominator, so this is our final form. So this set of fractions simplifies to this. Now, we may end up having to go the opposite direction, but for now, we're doing the simplification. So I'm going to finish these two examples in the next video, and so I will talk to you in the next video.